Hi there, this is Heath. I brought a friend today. We're starting week 9, which is on discrete dynamical systems. Let's get started. Just as a review, when we want to diagonalize the square matrix of A, we need to find the eigenvalues and we need to find the eigenvectors. Then we form a diagonal matrix D that contains eigenvalues going down its diagonal and then zeros everywhere else. I can list the eigenvalues in any order that I want. Then I create the conversion matrix P. They'll, of course, contain the eigenvectors along with the eigenvectors that we found. And the eigenvectors have to be in the same order as the eigenvalues that we chose. Then we need the inverse of the conversion matrix. And when we string them all together, PDP inverse, we get a breakdown of A into a conversion into an alternate coordinate system, a diagonal matrix in that alternate coordinate system, and then the conversion matrix back to the standard coordinates. What we're looking at today is the idea of a dynamical system in which we have an initial condition which is stored in some vector x naught. And then we have a transition matrix that explains how this system changes over some period of time. So A might be measured in change per year or per month or something like that. And every time we apply A, we get a new state of the system. So x1 would be one time period later, and we just multiplied A times x naught to get that time period. X2 would be 2 of these time periods later, but that's just A times x1 or A squared times x naught, and so on and so forth. And so at any given time t, we get a matrix that's A times x to the t minus 1, but that's the same thing as A raised to the t power times x. And if we want to describe what happens over a long period of time as t gets large, we don't want to have to multiply out A to the t. We would like to be able to use eigenvalues and eigenvectors to simplify that. That's the idea. We have a vector that represents the state of the system at any given time, and then we have this matrix A that represents how that state transitions from one time period to the next. Let's look at an example. We have a metropolitan area with a population of 1 million people. 600,000 people currently live inside the city. 400,000 people live in the suburbs. We can represent this initial population with this vector. So this is the population in the city at time 0, and this is the population in the suburbs. We have an annual migration matrix that says over the course of any given year, 95% of the residents of the city stay in the city. They were in the city at the beginning. They did not migrate. They stayed in the city at the end of the year. But 5% of the population migrates from the city to the suburbs over the course of a year. On the other hand, 3% of the population moves from the suburbs to the city, and 97% of the people in the suburbs stay in the suburbs. That's how this transition matrix works. These are in percentages. The columns tell me where they were at the beginning of the year. The rows tell me where they end up at the end of the year. So columns, beginning of the year, rows, end of the year. Okay. So if we want to figure out what the population is predicted to be 1 year later, this model says I can take this transition matrix, excuse me, 0.95, 0.05, 0.03, 0.97, and multiply it by the starting population. Apply the column row rule here. We get 600,000 times 0.95, 0.05, plus 400,000 times 0.03, 0.97. And when we add that together, we find that the population of the city has dropped somewhat and the population of suburbs has increased somewhat. That is, we now have only 582,000 people living in the city and 418,000 people in the suburbs. And if I want to predict what the population is 2 years from now, then I apply the state transition matrix to x1, which is the same thing as applying the transition matrix twice to x0, and we find that the population has shifted a little bit further, that a few more people have moved from the city to the suburbs. And so the pattern that we've seen so far, just looking at 2 years, is that the suburbs are gaining in population while the city is losing population. Is it possible to determine without just using brute force if the population of the suburbs will eventually exceed that of the city? Well, we know what the eigenvalues of this matrix are. They're 0.92 and 1, and these are the eigenvectors for this matrix. And so if we write our initial x0 as a linear combination of these eigenvectors, so x0 is equal to some constant, let's say c1 times negative 1, 1, plus some constant times 3, 5. Then a to the t x0 is equal to c1 a to the t times negative 1, 1, plus c2 a to the t times 3, 5. And the limit, as t approaches infinity, the long-term trajectory of this gives me a prediction of what would happen if we just let this model run indefinitely. But because these are eigenvectors, I can replace a with lambda. And so this becomes the limit as t approaches infinity of c1 times 0.92 to the t times negative 1, 1, plus c2 times 1 to the t times 3, 5. 0.92 to the t approaches 0, and 1 to the t approaches 1, and so we just get c2 times 3, 5. Now, we didn't take the time to figure out what c2 was, but what we know is that c2 times 3 is smaller than c2 times 5. And so we know just from answering this question, even without solving that c2, is that eventually, yes, the suburbs will gain population that's bigger than the city. And so, yes, the population of the suburbs will pass the population of the city. And we could, in fact, predict what that long-term value is approaching if we had taken the time to compute C1 and C2 up here. Let's look at another example. This is a predator-prey system. In the redwood forest of California, the main staple of the spotted owl's diet is the wood rat. This matrix models the monthly change in the owl and rat populations. due to population interactions, where the owl population is measured in owls, but the rat population is measured in thousands of rats, also called the killer rat. The current population is 20 owls and 8,000 rats. So that's my starting position. Okay? What do these numbers represent? A matrix that represents no change is the identity matrix. Again, rats are multiplied by 1,000 in this example. And so the 0.5 is smaller than 1. And so what that says is that the population of owls is decreasing by a factor of 50% if rats were not available as part of the diet. So in the absence of rats, the owl population would decrease by 50% each month. It's a decrease because it is smaller than the corresponding value of the identity matrix. What does the 1, 1 represent? Because 1.1 is larger than 1, what this says is that in the absence of owls, the rat population grows by 10% each year. Each month, sorry. This is a monthly change. The rat population would grow if the owls were not present to contain their population. This number is 10% bigger than the corresponding number for the identity matrix. So what do these two numbers represent? Again, here's the identity matrix. 0.4 is greater than 0. And it means that the presence of rats causes the owl population to increase at the rate of 4 owls, or sorry, 0.4 owls for every, my units here are in thousands of rats, so 1,000 rats. But this number is less than 0. And so the presence of owls causes the rat population to decrease at the rate of negative 0.1 thousand rats, which is the same thing as negative 100 rats for every owl. And this is again per month. So this is a classic predator-prey system, that the rat population would grow if left unchecked. The owl population would not, because the owl population needs rats to feed on. But once they are intermingled together, rats cause the owl population to increase, but owls cause the rat population to decrease. These are the approximate eigenvalues, and these are the approximate eigenvectors for this matrix. So what would this tell us about the system? Remember, our initial condition was 20 owls and 8,000 rats. And we could write that as a combination of these two vectors. And then the long-term behavior, the limit as t approaches infinity of AT times 28 is the same thing as the limit as t approaches infinity of C1 a to the t times 1013 plus C2 a to the t times 5,1. And because these are eigenvectors, we can replace a with lambda. C1 times 1.02 to the t plus C2 times 0.58 to the t times 5,1. And this term approaches 0, but this term approaches positive infinity. That is, this model predicts that the owl population and the rat population will both grow very slowly. I mean, this 1.02 to the t doesn't grow fast. It grows only about 2% each month. But over time, the owl population and the rat population will both approach positive infinity under this model. There is not enough of a check to keep these populations from eventually overflowing the resources of the forest. Okay? Let's do one more example. Let's use the diagonalization of this matrix here to predict the long-term behavior of this system. Okay? So what we're going to do, see if we can make this work. Is switch over to Wolfram Alpha, and we'll go ahead and work out the diagonalization of this matrix. I've entered the matrix. I've told it to diagonalize this matrix. And let's see what we get. So this is the interpretation. I want to point out a couple of things here. Our book uses P and D for the parts of the diagonalization, P for the transition matrix, and then D for the diagonal matrix, D for diagonal. For reasons that are not entirely clear, Wolfram Alpha uses S and J, but this is exactly what we've been doing, P times D times P inverse. And then here's your P matrix, here's your D matrix, here's your P inverse matrix. This matrix contains your eigenvalues, and this matrix contains your eigenvectors. So our eigenvalues are 0.2 or negative 0.2 and positive 0.5, and these are our eigenvectors. Let's go back to the problem and see if we can make that work. Let's go back over here. So our eigenvalues were negative 0.2 and positive 0.5. Our eigenvectors were negative 0.75, 1, and 1, 1. And so I don't know what x naught is. They didn't tell me what x naught was. They just told me what A was. But the long-term behavior, as time approaches infinity, of xt is the limit as t approaches infinity of a to the t times your initial condition, which is a to the t times some linear combination of these two eigenvectors. I'm going to distribute the AT and go ahead and replace the A with the lambda. So we get C1 times negative 0.2 to the T times 0.751 plus C2 times 0.5 to the T times 1, 1. This term approaches 0, and this term also approaches 0. And so it didn't matter what our initial condition was. It doesn't matter what x naught is. No matter what the initial condition is, this system will always approach the origin over time. Because both eigenvalues, when we raise them to the t power, both eigenvalues approach 0. And therefore, it doesn't matter what the initial condition is. The initial condition is that the system will always, always, always approach 0. All right? Y'all take care. Bye-bye.